Okay, hello again everybody, and today we'll be doing organic chemistry. And this is a branch of chemistry that studies the structure, properties, and reactions of organic compounds which contain carbon in covalent bonding. So they're primarily carbon-based compounds. In organic chemistry, we have what are known as homologous series. A homologous series is a sequence of compounds with the same functional group and similar chemical properties in which the members of the series can be branched or unbranched. The functional groups are specific substituents or moieties within the molecules that are responsible for the characteristic chemical reactions of those molecules. So let's go ahead and get right into it with our first homologous series known as the alkenes. Known as alkanes, and they have this general formula CnH2n plus 2. So what this means is that if we have one carbon here, single carbon, then we're gonna have 2 times 1 plus 2 hydrogens, which is 4. This alkane is known as methane. The way we name this is firstly we look at how many carbons there are. So there are prefixes to correspond with different carbon numbers. If we have one carbon, it's meth, 2 eth, 3 prop, 4 bute, 5 pent, 6 hex, 7 het, 8 non and dec would be for 9 and 10. So with the number of carbons we have, and so we have one carbon, so we have meth, then we have ane suffix because it's part of the alkane group. Let's look at a few other. Wait, the structure of this alkane, by the way, would be CH4 with the carbon in the middle and 4 hydrogens surrounding it. Let's look at another one called ethane. Now, if it's called ethane, that means you would have 2 carbons. And then, to get the number of hydrogen, you would multiply 2 times 2 and add 2 to that, so we get 6. And that molecule would look something like this. It is important to know that carbon cannot form more than 4 bonds. So here we have this carbon, it is bonded to this carbon and 3 other hydrogens, so that fulfills the 4 bonds. One of the primary characteristics of alkane is that it's fully saturated, so there are no double bonds. All the carbon bonds are filled. Of course, we could just go ahead and keep on adding more and more carbons. And by doing that, we could make say propane gas, which is very useful in terms of gas stoves. Or we could remove this, add another carbon, and make butane, and so on and so forth. Now let's look at alkenes. Now alkenes are very similar to alkanes, but they have a slightly different general formula. This general formula is CnH2n, And the reason for the reduction in number of hydrogen atoms is that alkenes are characterized by one carbon to carbon double bond. So, firstly, what that means is that there is no methane because there need to be at least two carbons for the carbons to be double bonded to each other. So, alkenes start at ethene. And let us write the formula for that. So, it will be C2H4. And the molecule would look something like this. Now notice here we have two of the carbon bonds filled, and then we have carbon being bonded to one hydrogen and then being bonded to another hydrogen. So overall that makes four bonds filled for both carbons. And you also notice that the hydrogens aren't placed directly above the carbon. This is because this is the optimal shape for the molecule when the double bond is present. And so we could, like alkenes, we could just add more carbons, and then we could just go ahead and continue the molecule just like that. Again, you notice we have three carbons, six hydrogen, so Cn, H2n. That's for the alkenes. Now let's move on to the alkynes. Alkynes, similar to alkanes and alkenes, but they're characterized by a triple bond, and so they have the formula CnH2n minus 2. Again, you cannot have methane as we require at least two carbons to have a triple bond. So we could start from ethane. So ethane would be C2 and we would have H2n minus 2 which will give us H2 and the molecule would look something like this. Then we would have one H there and another H over here. And then of course, just like the others, we could just add more carbons, add more hydrogens, fill like that. Now let's move on to a homologous series which possesses a functional group. First one we'll be looking at is alcohol. Alcohol. This is the general formula CnH2n plus 1 OH, where OH or hydroxyl is the functional group that characterizes it as an alcohol. So let's try write methanol first. So we'll have one carbon, then 2 times 1 plus 1 is 3. So we'll have H3 OH. And this methanol, this is a very toxic compound. The molecule will look something like this. Now, OH is said to be terminal, meaning that it should always be at the end of the chain. So let's say that we wanted to right, very long chain of alcohol. Let's say we had butanol. By the way, alcohols only possess single bonds. So we have H's there, hydrogen is all over, and then the OH group would always come at the end of the series. So it's known as a terminal OH group. Alcohols are very useful compounds. Ethanol is the same alcohol that is used in beverages like rum and beer. Propanol is alcohol normally used as rubbing alcohol. Now let's look at our final homologous series called alkanoic or carboxylic acids. Or you sometimes hear they be referred to as organic acids. And these are usually weaker in terms of strength of acidity than inorganic acids such as sulfuric acid or phosphoric acid. Now, the general formula for these are CnH2n plus 1 COOH. Now, what you must know is that carbon that forms the COH group or the carboxylic group is a part of the full carbon structure, which means that we have to take this carbon into account when we are naming the compound. Therefore, if we have C3H7 COOH, this would actually be butanol because you have to take this carbon into account to say it's actually a 4 carbon compound. And the way the molecule would look would be it would look something like this. And then we'd have a double bonded oxygen, and then oxygen bonded to a carbon and a hydrogen. And this right here is the carboxylic group that allows this to be an acid. It's a combination of what is known as a carbonyl group that we'll learn about at a different time, as well as a hydroxyl group. Now let's look at reactions of some of these compounds. And we start with substitution reactions. So substitution reactions, of course, is when the hydrogens in the compound get replaced by other molecules such as halogens. So we look at halogenation, which is where one of the halogens replaces hydrogens. Let's look first at alkanes. Now, alkanes are very saturated. Alkanes are saturated compounds. Let's draw methane. As you'll see, all the carbon bonds are filled. They're all single bonds, and so there is no space in which to add anything. You can only replace. Therefore, alkanes only go through substitution reactions. And one such reaction is the reaction between methane and chlorine. And what will come of this reaction By the way, the catalyst for the reaction is UV light. Light is required to split the hydrogen bonds between the hydrogen and the carbon. UV light. What will come from this is we'll have TH3Cl. In other words, one of the hydrogens will be replaced by a chlorine atom, and so we'll end up with H2 gas here. Now, of course, this isn't balanced, but you get the idea. And what will happen is that if we leave it, the reaction will progress, and we'll eventually get this reaction CH3Cl plus Cl2. The reaction is progressed with excess chlorine. We get this reaction and we'll end up with CH2 Cl2 plus hydrogen. Now, if we allow it to continue, it will eventually replace all of them until it reaches carbon tetrachloride or chloroform. And of course, this is a very dangerous compound. Most of these compounds are highly dangerous, so not to be played with. Now let's look at with alkenes. So we have the alkenes. As you know, the alkenes have a double bond present. What that means is that there is space left for other molecules to actually attach themselves to the compound. Therefore, they can undergo substitution as well as addition reactions. So, if we look here, we'll see that these carbons are double bonded to each other, but they can't stretch those bonds. So what happens is that we can get rid of one of the bonds. Therefore, both carbons now have an empty space to which we can attach other molecules. Again, we could actually attach halogens. So a reaction between a bromine and ethene would produce a molecule looking like this, where bromine fits itself into the molecule. And when this happens, when we're naming the compound, we would now give it the name of an alkane because it now has complete single bonds. And we would actually call it 2-bromoethane. Okay, that's all for this video. I'll see you all next time.
Tell me pretty lies, look me in the face. Tell me that you love me, even if it's fake.